Welcome back, everybody. So today we're going to talk about non-equilibrium carrier densities in semiconductors and recombination and generation. And this is one of the most important topics in terms of devices because all of our really interesting devices actually work because of these minority carriers. And making sure that we understand their dynamics is extremely important and is really at the root of understanding how the devices actually work. So first we can start with a few definitions. So we've talked previously about the doping in semiconductors and thermal equilibrium quantities. So from now on we're going to start adding these subscript knots, which will denote the equilibrium quantities. And let's just go back and review. A semiconductor in equilibrium actually has a lot of different processes happening. So let's take an N-type semiconductor, for example. There's actually constant cycling of electrons between the donor levels and the conduction band, but also there's the spontaneous recombination and generation that occurs because of thermal energy, where electrons are generated from the valence band up to the conduction band and then spontaneously recombine and fall back down to the valence band. And these equilibrium quantities, N naught and P naught, because we can write them in as the N naught P naught product being a constant, Ni squared, indicates that this is a situation of dynamic equilibrium. It's not static equilibrium. There's constant generation and recombination processes happening all the time. So what we're going to look at now are processes where we can disturb this thermal equilibrium. So one process would be if we shine light on the semiconductor, we shine in a photon and absorb it. This generates a delta N and a delta P because we had to steal an electron from the valence band and move it up to the conduction band. And now we no longer are in the same condition we were before of thermal equilibrium because we've added an exterior stimulus to the semiconductor. Another way we can add excess carriers is, let's imagine we have some current flowing, and we're going to say this is the current carried by holes. And on the other side here, we'll call this in. So if we have a small region in space of our semiconductor and we have some holes flowing in and some holes flowing out, we can actually build up excess carriers in that region if these two currents are not equal. So we can either move carriers through the semiconductor and accumulate them or drain them, or we can have light shining on the semiconductor. So either currents, light, or other particles. For example, if you're working in radiation detectors, the radiation can actually generate these electron hole pairs also. So any exterior stimulus that can disturb this equilibrium will generate these excess carriers. So we have to define sort of dynamic or time-dependent carrier concentrations. And the nice way to do this is to recognize that our N naught is time independent. And so we can add this disturbance to that equilibrium, this delta N, and deal only with the time dependence of this part. Similarly, for our hole concentration as a function of time. We'll write it this way. Now, for processes like this one, where light generates the excess carriers, we can always know that delta n is going to equal delta p. And that's because we generated one hole and one electron when one photon was absorbed. In terms of currents, this may not be the case, because it is possible, especially in heterostructured semiconductors, to have current carried entirely by holes or entirely by electrons. Such that the delta n is not necessarily equal to delta p. So I put the question mark there because you're not sure if that's true. So most of the time, we're going to consider processes like this, where you shine light on the semiconductor, and you can make this assumption. So in the following, we'll be using this assumption, although we need to remember that this general case might apply under some situations. Let's take an example in which we have a p-type semiconductor. And we're going to define another set of ancillary variables. So we have our Fermi energy here, closer to the valence band. And we have P naught and N naught. And then let's come in with some light, for example, and generate some delta N and delta P. So it turns out that the Fermi level can only describe a situation of thermal equilibrium. The Fermi level was defined in terms of the equilibrium statistical mechanical distribution of electrons and holes through this band structure. And so if we want to still be able to write equations like n equals nc exponential to the negative EC minus EF over kBt, these ancillary variables, which are the exponential transform of the hole, the hole in electron density, we can still do that, but we have to define now a new quantity called the quasi-Fermi level. So the quasi-Fermi level pertains to situations out of thermal equilibrium. And we can also write a similar equation for the holes. And we define that as EFP. So the quasi-Fermi levels are now different for the electrons and the holes. So let's return to this situation. So if it's a p-type material, we know that the p naught is much greater than the n naught. So for example, if we have number of acceptors equal to 10 to the 16 per cubic centimeter, if we use this relation, the n naught p naught product has to be constant, we find out that there's 10 to the 4 per cubic centimeter of the electrons. So there's so many more. Now, let's ask the question, is this delta n that we're going to impose bigger or smaller than n naught and p naught? So we can define two conditions, actually. Low injection, where delta n, and in this case, delta p, because we're talking about photon generation, is much less than p naught. So p naught is the called the majority carrier concentration, because there's more of the holes than there are of the electrons. And then, as you can probably guess, the other regime is high injection, where delta N is greater than, or actually equal to, P naught. So when the excess carrier density starts to approach and become an appreciable portion of the total holes, you have to revert back to high injection. So most cases are going to live in this low injection regime, and most of our device behavior, our most common case is going to be low injection. And it's nice because this allows us to simplify a lot of the equations. So let's try to place these quasi-Fermi levels here on this band diagram. So if you look at this first relation for low injection, which we're going to assume here, for low injection, the excess carriers are a small perturbation on the total carrier density. And so we can say that the EFP is about equal to the original Fermi level. However, in this example, let's imagine that we have delta N somewhere around 10 to the 12 per cubic centimeter. So 10 to the 12th is much, much bigger than this 10 to the 4th, and this is where the action really happens. So now we have to move our quasi-Fermi level for the electrons by a significant amount in energy. And this distance here would be called the splitting of the quasi-Fermi levels. So a semiconductor that's out of thermal equilibrium, because it has excess carriers, will have quasi-Fermi levels which are split. And that's sort of just a transformation of the statement that the semiconductor is out of thermal equilibrium. And it's a logarithm, the quasi-Fermi level splitting is a logarithmic measure of the departure from equilibrium, the degree of departure from equilibrium. Okay, so now let's start to dig into the math. And first we're going to work on determining how the excess carrier concentration will return to equilibrium, how the system will relax. So first we want to work out some math within the so-called lifetime approximation. We want to be able to write a differential equation for how the carrier concentration returns to its equilibrium state. Remember our definition that the N naught is constant, so we can absorb all of the time dependence inside the excess carrier concentration. First, we want to sort of think about the physical process by which the system will relax. So when our photon came in, we generated some electron hole pairs. And then you'll notice that I'm using the green and red markers. The recombination is the reverse process, where these electrons and holes disappear. And you'll notice that both of these processes involve one electron and one hole. So we should intuitively think that the rate of their disappearance should be some constant times the product of N and P. And then we know that all of the carriers won't disappear. You'll only return to the equilibrium state. So the total carrier concentration will decay back to the equilibrium concentration. And we know that the proportionality, there should be a negative sign here because the carrier concentration doesn't amplify, it decreases. So let's expand out these terms and simplify this. So we have n plus delta n times p plus delta p, and then minus n naught p naught, but we know that this is ni squared. So we have, oops, I forgot some knots, n naught p naught plus p naught delta n plus n naught delta p plus, and then minus the ni squared. So again, we use this relation to cancel these terms, that these two are equal. And now this is the general form which can apply in any situation. So in the next line, I'm going to use the idea that our delta n and delta p are going to be the same. And then substitute in here. So we have p naught delta n plus n naught delta n plus delta n squared. Now let's return to our p-type semiconductor. So now we have that n naught is much less than p naught. And then if we look at these two terms here, if n naught is less than p naught, we can neglect this term. And then if we make another assumption that we're in low injection, we can also neglect this term, delta n squared, with respect to this term. So in the end, our final result is that d delta n of t dt is negative constant times p naught times delta n. If we move this over here, we can see that we have a 1 over delta n d delta n dt, which is the same thing as d logarithm of delta n dt, and this is equal to negative constant times p naught. So the solution of this differential equation here is an exponential. So the delta n of t is now given by delta n of t equals 0 exponential to the minus t over a lifetime tau. This is where the lifetime approximation gets its name. And this tau, sometimes called the minority carrier lifetime, is equal to 1 over this constant times our p naught. And if we go back to our definition of p naught, this would usually be written for normal operating conditions as constant times Na, with the assumption that Na equals p. So this is the basis of our approximation that we can represent the dynamics of these excess carriers as exponential in time. You see from the full math treatment And the fact that we had to invoke a couple of assumptions here, for example, that the doping is large enough that we can make this assumption, and that we're in low injection conditions, that in the general case, for example, in high injection or intrinsic semiconductors, this lifetime approximation will not be valid. But let me reiterate, for most cases and most devices, this is the form of the equations that we can use. Now that we've derived the lifetime approximation, let's look at the continuity equation for excess carriers. What I'll do here is sort of a physical derivation instead of a full derivation, concentrating on the ideas here. So we have an infinitesimal volume, dx, dy, dz, and we're going to monitor the n equals n naught plus delta n inside it. So we can have some currents flowing in and out from 3 different directions. And if the currents in are larger than the current out, we'll accumulate some carriers inside here. So we know that in this control volume here, there has to be a term proportional to the difference of these 2 currents, which turns out to be the derivative of the currents, or the div of the vector currents. So we can accumulate carriers this way. We can also come in with some photons or other particles that are ionizing radiation and generate some excess carriers. And then lastly, we can have the opposite process of recombination. And we're going to write our recombination within this lifetime approximation as this form, so that you have some recombination rate which is proportional at any time to the number of excess carriers. So I'll make this substitution. And we can write a similar equation for the holes also. So then let's look at this term here. So our currents, which we talked about in the last section on transport, are going to have drift plus diffusion components. The drift part is driven by the E field. The diffusion part is driven by a concentration gradient. So we can write the first one as E mu n times n plus E mu p times p, and then all of this times the E field. And I'm just going to go from our 3-dimensional form to 1-dimensional here. And then the diffusion part is minus d. So this is the general form. I'm writing it out for both electrons and holes in the first line here. So we can consider the electron and holes parts of both of these. Let's now consider just one of these. So let's take the n-type part and just follow through the math so that we can look at what happens when you have to take this spatial derivative in your continuity equation. So I'm going to write in 1 dimension the derivative of the n-type current. So this is going to be E mu n times d by dx of the product now of n and E. And then minus d by dx of dn dx. So it's usually assumed that the diffusion coefficient is a constant and does not depend on the on space in this little volume we're talking about, or on the carrier concentration. So we can reduce this one to d times the second derivative with respect to distance. But this one, it turns out we have to keep the dependence here, because you get a funny behavior where you'll see if there's any gradient in the E field, as there is inside of a p-n junction, for example, you'll have the normal derivative that we expect. So dn dx times E, this we expect, but there's another term that arises, which is n dE dx, that we can't forget about. So in regions where the electric field is changing versus distance, for example, in a p-n junction, if we have band bending here, so if this is our E, EC, EV, and the bands look something like this, in this region here, the depletion width, our E field actually changes versus distance. So this would be your E field, and it's negative, and then versus x this way. So in these regions, you'll get this extra part to the accumulation of excess carriers. So carrying through that derivation and plugging our results into the continuity equations. So we've used the lifetime approximation here for the recombination rate. We can get these two differential equations. The drift portion is here, the diffusion portion is here, generation, recombination equals our total time derivatives of the carrier densities. And notice these are the total carrier densities. So if we can say that n naught and p naught are not functions of x, and we know already that they're not functions of time, so then we can actually substitute in our breakup of the total carrier density into the excess carrier part and the static part, and just put delta n everywhere we see an n here. And similarly for delta p there. So as long as we're in a region where the doping is constant, so then these two equations are the equations that govern our total dynamics of our excess carriers. This is how they move through the crystal, and then in any given place, they can either be generated or annihilated. And so we can keep track of their numbers in both space and time this way. So we're going to break here, and in the next section, we'll talk about a little more specific information about the mechanisms by which the recombination happens inside the semiconductor.